All right, AP Physics C. We got one student in the classroom.
What's up?
He's about 20 feet away from me. So I'm downing this thing, deflecting my breathing down. All right, so vectors. Let's take a look at this problem here and make the video, post it. If there's a question in class, okay, technically you can't say your name. But if you have a question, just speak up and we'll get to it. So I'm not going to project it. I'm just going to look at it on my computer screen here. Lost space probe has a constant velocity. So now we've done this a bit in class. I'm going to write pretty large here so we can see it. 5i hat minus 2j hat plus 4k hat. All right. So this is a constant velocity in 3 directions, right? So this is kind of tricky. We can try drawing this. All right. I'll see what we can do here. I don't know if this is going to come through on the video or not. We actually draw 3 dimensions here. Now, it would have been nicer if I had made this just positive. Right? It would have been easier to draw. Okay, so you can kind of see that. All right, so the x component of velocity is 5 meters per second. So that would be, I'm going to draw it with thicker dash. That's the x component of velocity. The y component is -2. And the y-axis is this axis, actually. You make this the xy plane. Right? Make a parallel here. But the z-axis, the z velocity here is +4. All right? So now I kind of make like a rectangular prism out of this to try to visualize where the velocity vector is pointing, right? Velocity vector is going back into this quadrant here, pointing back towards this side. Oops, I drew it wrong. Pointing back to that corner. The way we draw it is we try to make it thicker here because then it's getting thinner out there. Didn't really translate. It's going back to that back corner, the velocity vector. It's a little bit hard to see, definitely. I didn't ask you to draw it because it is so hard to draw. That's the way it's going. Determine the probe speed. Probe speed is the magnitude of this overall vector. This is Vx, Vy, Vz, and the length of this vector is the speed, v. Now, how do you figure that out? Normally, we just use Pythagorean's theorem with the x and y component, right? We do square root of the x component plus the y component, each of them squared, obviously. So we'd say the speed, v, which is the magnitude of the velocity vector. So if you want to take the magnitude of a vector, you can just leave it a v without the arrow over it, or you can take the actual magnitude simply. You know that one?
Yeah.
Okay. And it's going to be equal to the square root of, now somebody had written me and said, I don't know what to do with that k hat. Well, it's pretty interesting. You just add it in like that. You can do Pythagorean's theorem in 3 dimensions. And I can prove that to you kind of quickly right now. So, ultimately, this is the triangle we're trying to find the hypotenuse of. It's one that kind of goes diagonal through this cube, right? That's it. So this height of the triangle is Vz. What's the base of the triangle? Well, the base of the triangle is the hypotenuse of the triangle in the xy plane, right? This is Vy. This is Vx. So check this out. It's kind of cool. V squared, how much room do I have? Okay, V squared, this hypotenuse is VZ squared plus whatever that is, right? V squared, whatever this height is. Well, that height, right? That squared is equal to V squared, Vx squared plus Vy squared. So you end up getting velocity squared is Vz squared plus Vx squared plus Vy squared. So that's kind of a cool result. It's Pythagorean's theorem in 3 dimensions, and you do it in 2 steps. You find the hypotenuse of this triangle, then you use that hypotenuse here, right? I call it dxy, becomes the base of this triangle, gives us v. So that's how you do this. When you do the math, I forget what you get here. Second square root of 5 squared.
You get 45.
You get what?
45.
I got 6.7. Was that before you took the square root? Probably.
I don't know, probably.
25 plus 16 plus 4, yeah. Yep. So they actually take the square root of it in the end, you get a speed of 6.7 meters per second. Now you could find angles, that'd be a pain though, right? Because actually you'd have to find this angle and this angle. You actually have to find 2 different angles to get that position. This is why we use vector notation, so we don't have to go through and find these angles. All right, so what's the probe's displacement after 2 hours? Please write in vector format. All right, so I'm going to erase this here. Oh, this marker erases a lot nicer than the Expos. Holy cow. So displacement, now you can't use delta x for displacement because we have delta x, delta y, and delta z, right? So what we end up using for displacement is delta r. Delta r is displacement. Displacement vector is equal to the velocity vector times time. All right? Well, we can literally put in 5 I hat. Now, if you go and just do this times time of 2 hours, or 2 hours would be 7,200 seconds, you would get the distance traveled. That's not the displacement. The displacement, you'd have to have the magnitude and direction, or you just write it in vector format, because technically displacement's got to be a vector quantity. All right? So 5i hat minus 2j hat plus 4k hat, and you actually just multiply it by 7,200 seconds. And when you multiply a vector by a scalar like this is a vector multiplied by a scalar quantity, you just scale up each coefficient to actually distribute the 7,200 to each term. So you get the displacement vector, delta r we're calling it again. You know, it'd be the same diagram as the last one, right? With this weird vector going off in the back quadrant. And we call it r because it's x, y, and z all combined. So here now we've got 5 times 7,200. That's 36,000. I hat minus, what is that, 14,400 j hat. And then 7,200 times 4, I'm not smart enough to do that. Well, I guess I am. 28,800, right? Plus 28,800 k hat. All right, so there's your displacement vector. And you can just leave it like that. It's in terms of meters, as is. So that's a displacement vector. You don't have to combine that. Now, for the next question, it says, how far from the starting point is it? Well, then you do have to find the magnitude of that vector. The length of that vector will tell us how far in a straight line it's gone to that point in that corner. Right? So, the actual distance it's traveled, which we're just going to call r, is the magnitude of this vector, which is going to be square root of 36,000 squared minus 14,000 squared plus 28,000 squared. All right. So unfortunately, that's a big mess in the calculator. I should have made it move for like 2 seconds rather than 2 hours. That would have been nicer. But you know, I figure space probe, you know, let's let it move for a long time. We've got a couple satellites that have been not satellites, space probes that have been traveling through outer space since the 70s, and still making contact. They actually left our solar system technically, just outside of it. All right, this gives me about 43,400 meters. Is that what you've gotten?
Yeah.
43,400 meters in a straight line. So again, if I want to try drawing a picture of this, it's kind of a pain. It's actually going back, right? So it's going this way, and back that way, right? So it's like some weird vector going off into the back corner of this coordinate system. I'm not going to take the time to draw it fully right now. It looks a lot like the last drawing. Now this next part says, okay, let's give it an acceleration. So let's say in an attempt to recover the probe, engineers fire jets, give the probe an acceleration now. All right. Erase all this. Get rid of this. All right, I'm going to give it an acceleration of 2I hat, 2J hat, negative K hat. 2I hat plus 2J hat minus K hat, which is there's a 1 that's implied there. What will the velocity in vector notation be after 5 seconds of firing the jets? So V final equals V initial plus AT. And here's the trick. If you took AP Physics last year, you know that these equations are bold, or those variables are bold. That meant they were vector quantities. So here's what we do. The final velocity vector is equal to the initial velocity vector, 5I hat minus 2J hat plus 4K hat plus the acceleration vector, 2I hat plus 2J hat plus 1K hat times time, which we said was 5 seconds. 5 seconds. Cool. And we really, okay, so we distribute the 5 through here. Then we group like terms. That's going to give us our final velocity. This is so much easier than doing, you know, like we did last year where we said x direction, y direction. Well, we'd have to make a table for x direction, table for y direction, table for z direction. But if we just do this vector notation, we just do it all at once together. And then when we want to find the final magnitude of the final vector, we just do Pythagorean's theorem. We're good. Good stuff. So anyways, distribute the 5. So I'm going to start writing this all out. The final velocity vector. Remember, this was our initial velocity vector. This was our acceleration vector. So our final velocity vector is 5I hat minus 2J hat plus 4K hat plus 10I hat plus, oh, this was supposed to be a negative there, I almost made a sign error, plus 10J hat minus 5K hat. Now, I haven't written units down, but if you think about it for a second, each one of these coefficients on here would be meters per second squared. So meters per second squared times seconds, that gives meters per second. So all these coefficients have the same units, so we can add them together. All right, so you got to be careful there. And you can only add like terms, right? That makes sense. So like terms being 5i. So this is this is just algebra, really. You're treating these like variables, I, J, and K. You can group like ones, just like you would in algebra. So V final ends up being equal to 15 I hat plus 8 J hat minus 1 K hat. And then how fast will the probe be moving? That's the final velocity vector. The speed, which is the same variable with no vector over the top, no arrow over the top, is simply apply Pythagorean's theorem. So square root of 15 squared plus 8 squared plus 1 squared. I never write, some people will write plus -1 squared. I know that is always going to come out positive, so I don't bother with that. I just pull the coefficient without the sign, put it in there. Obviously, I know if it's negative and you square it, it's going to come positive. So I just do it like that. So then we'll get the final mathematical answer: 15 squared plus 8 squared. Oh no, syntax error. Square root of 290, which gives me about 17 meters per second. Final velocity, final speed. And the angles, you don't want to have to find the angles, right? Because you got to find two angles, one relative to the horizontal plane, one relative to one of the horizontal axes. Vertical plane, sorry. Vertical axes. That'd be a big pain. So that's it for that question. Hopefully that gets you going and clarifies some things for you. Talk to you guys later. Hope you enjoyed the face shield. Yes? Yes.